Today, we are stepping into the computational ring for a title fight that, believe it or not, underpins almost all of modern science and engineering. We're talking about the epic challenge of solving massive, and I mean massive systems of linear equations. So let's get right to it.
Think about the biggest computational problems you can imagine. Simulating the airflow over a new jet wing, forecasting a hurricane's path, or even training a really complex AI model. They all seem like totally different worlds, right? Well, it turns out they all share a secret mathematical heart.
And that's the secret. Every single one of those monumental tasks gets done by solving not one, not 1,000, but millions, sometimes even billions of interconnected equations all at the same time. The scale is it's mind-boggling, and that's exactly the problem we're going to break down today.
Okay, so how in the world do you even write down a billion equation problem? Well, it turns out the whole thing can be boiled down to a form that's just beautifully simple and incredibly powerful.
And this is it. This is the main event. A is this giant matrix, basically a massive grid of numbers that describes all the relationships and all the physics of this system. B is a list of the knowns, the outcomes or forces we're applying. And X, well, X is the list of unknowns we are trying to find. Solving for X is the key to absolutely everything.
So, how do we solve for X? Well, our first contender in the ring is a direct, kind of brute force approach, a method that's designed to finish the fight with a guaranteed, perfectly precise answer.
And the philosophy here is what's really key. A direct method follows a strict step-by-step recipe. It doesn't guess, it doesn't approximate, it just marches through a predetermined series of steps, and at the very end, boom, it hands you the exact solution.
And in the world of direct methods, one name really does reign supreme: Gaussian elimination. It's a total classic, a powerful algorithm that you might have even bumped into back in school.
It works in two main phases. First up, you've got forward elimination. This is where you systematically combine equations to zero out entries and turn that messy matrix A into a nice, clean, upper triangular form. Then comes the elegant part, back substitution. See, now the last equation only has one unknown, so you can solve it easily. Then you plug that answer into the second to last equation, and you just keep working your way back up to the top. It's so clever and so effective.
But, and it's a big but, here's the catch. For really big systems, this reliable workhorse has a huge appetite. It can be incredibly slow, and it demands an enormous amount of computer memory. This is especially true for what we call sparse systems, where most of the numbers in that big matrix A are actually zero. For our billion equation problem, the finisher often just can't go the distance. And that brings us to our second contender. This is a totally different approach. If the direct method is a knockout artist going for one big punch, this one is more like a clever strategist, built for endurance and efficiency.
And this slide just lays it all out perfectly. Instead of following a long recipe to get one perfect answer, an iterative method starts with a guess. Literally any guess will do. Then, in each round or iteration, it uses that current guess to cook up a slightly better one. It slowly, strategically, inches closer and closer to the real solution, round after round.
And there isn't just one strategist, there's a whole team of them. You have the Jacobi method, which is pretty patient. It calculates all the new pieces of its next guess using only information from the complete previous guess. Then there's Gauss-Seidel, which is a bit more eager. As soon as it calculates a new value for one variable, it immediately uses that fresh, updated value to calculate the very next one, all within the same iteration. And then SOR is a variation that tries to be even smarter, adding this relaxation factor to try and speed the whole thing up.
Okay, this guessing and refining strategy sounds fantastic for those big, sparse problems where direct methods just fall flat. But it does come with one huge question. How do we know the guesses are actually getting better and not just wandering off into space?
And this is absolutely the crucial point. Unlike a direct method, an iterative solver can just fail. It might not converge, the guesses could get stuck, or even fly off toward infinity. So for our strategist to have any chance of winning, the fight has to happen on favorable terrain. The question is, what does that terrain look like?
Well, one of the most important conditions is something called diagonal dominance. It's a bit of a mouthful, but the idea is simple. It means that for every single equation in our system, the main variable's coefficient, the number on the diagonal of the matrix, is bigger than all the other coefficients in that row combined. When a matrix has this property, the whole process acts like a contraction. Every guess is guaranteed to pull the solution closer to the real answer. It's a huge sign that our iterative strategist is going to succeed.
But there's an even deeper, more fundamental way to predict success, and even speed. To really understand the behavior of these methods, we need to look at the soul of the matrix A, its eigenvalues and eigenvectors. An eigenvector is just a special direction, a special vector that when you apply the matrix to it, doesn't change its direction at all. It only gets stretched or shrunk. And that stretch factor, that's the eigenvalue, lambda.
So what does this have to do with anything? Well, think about the error in our guess. It turns out that error gets reduced with each iteration, and the rate of that reduction is controlled by these eigenvalues. The biggest one, called the spectral radius, is basically the ultimate speed rating. It tells us how much the error is shrinking in the worst possible direction. If that number is small, the error disappears super fast. If it's close to 1, well, we're in for a long, slow fight.
So, after all the rounds, after looking at all the angles, who wins the showdown? Is it the finisher or the strategist? It's time to go to the judge's decision.
And when you look at the scorecard, the results are pretty clear. Direct methods, they're the undisputed champions for smaller problems or dense ones where you absolutely need a guaranteed exact answer. They're predictable, but they just get way too slow and memory hungry for the big leagues. On the other hand, iterative methods are the go-to champs for the huge, sparse problems that define modern science. They use way less memory and can be dramatically faster, but only if the problem has the right properties to make sure they actually converge. So what's the real takeaway here? It's that there is no single winner. It's not about which method is better in a vacuum. It's all about which method is the right tool for the specific job you have in front of you. The real art and science of this field is being able to look at your problem, at your matrix A, and choose the solver that's going to be the most effective. You know, the ideas we've talked about today, from Gaussian elimination to these iterative solvers, they are the absolute bedrock of scientific computing. They've been sharpened and perfected for decades, which leaves us with one final thought to chew on. As we push into brand new frontiers like quantum computing, global-scale AI, and simulations of insane complexity, what new challenges are waiting just around the corner? And what will the next generation of solvers even look like? Thanks for tuning in.